Hi everyone, in this video I'm going to demonstrate how to use GeoGebra to calculate the area underneath a particular function. In this case I've graphed a periodic function f of x equals 2 sine 5x plus 6. So the first one I want to demonstrate here is the definite integral. So the command is integral, and as I start typing I get these suggestions. The one that I like is this third one here. So specify the function, the start and the end value. Just to left click on that. Now the function is referred to by name. In this case it's f. It could be anything you'd find. Right arrow across to start value. Let's say we start with value 1, end value of let's say 5. Now here is my integral. Press enter. The area is 23.72 square units, starting from 1, going to 5 like I asked. There's the area displayed, and it's a perfect match. It follows the curve exactly. Exactly how GeoGebra calculates this I'm not sure. I think it's probably a Simpson's rule type of a calculation, but it would be the same answer as you got if you did the definite integral and worked it all out algebraically. Just turn that one off for a moment. The next one I want to demonstrate is if we were to do a Riemann sum, which is splitting the area up into a series of rectangles. The command is rectangular sum. As I start typing, here's the suggestion. So left click. Function again is referred to by name f. Right arrow, the start value. For consistency, I'll stick with the start value 1, end value 5. The number of rectangles. Let's go 20 rectangles. That's a fairly high number. And the position, I'll start with 0. Now, you see here that the area calculated is 23.58, just a little bit lower than the true value of 23.72. So what's going on? Well, you can clearly see on the diagram here. Just let me turn off the grid for a minute so it's clearer. There we are. Now, each of these rectangles starts at 1, goes to 5. It's a difference of 4 steps across the x-axis. I had 20 rectangles, so 4 divided by 20 would be the same as 1 over 5. Each of these rectangles is decimal 2, so that's 1.2, 1.4, 1.6 and so on. Now what does this 0 stand for? That tells GeoGebra to use the value of the function at the left-hand side of each rectangle. So between 1 and 1.2, it picks the value of the function when x equals 1 and draws the rectangle straight across. We call this the left-hand sum, and so clearly some of these rectangles are underestimates, a few are overestimates. Hopefully, if we're lucky, the under and the overestimates will counterbalance one another. They seem to have pretty well, and we have a close answer. This is only approximate, of course, but the great advantage of this is that it's very, very simple to calculate, especially for a computer. I can increase the accuracy if I were to increase the number of rectangles. I don't have to say 20, I could say 100 rectangles. Now, each of these rectangles follows the same rule, the left-hand side of the little width there. This time the discrepancies are much, much smaller, and my answer is much, much closer to the true value of the area. So rectangular sum or numerical integration is a perfectly good way to calculate the area under a curve, but for the purpose of demonstration and to make it easier to see, I'll stick with 20 rectangles. A bit chunky, but it's easier to understand. Now, what does this last parameter 0 do? I've explained that that gives the rectangles on the left. What if I change that parameter to 1? All of a sudden, my rectangles are now drawn on the right-hand side of the interval. So this first rectangle, I calculate the value of the function at x equals 1.2. Draw the rectangle across the top there as if it was the value at 1.2, and then calculate that area, likewise for the rest of them. Again, some are going to be over, some are going to be under, and the combined estimate this time is still not too far off. This time it's a little bit larger. Well, next obvious question, I suppose, is what happens if we put 0.5? 0.5 gives the midpoint of the interval as the height of the rectangle. This time we get an answer which is very close. Not exact again, because it's still a numerical estimate, and the little bit here which is above is not exactly going to counterbalance this little bit that's missing, and likewise for all the other rectangles, but it's certainly a pretty good approximation. And again, very simple to do. So this rectangle sum function is really three different ones combined: left, right, or midpoint, depending on the value of this parameter that you choose. The next one that I want to demonstrate is called the trapezium rule. So we start by typing trapezium. Here it is, trapezoidal sum. The function, again, f for the name of the function. Start value 1, end value 5 for consistency. Number of rectangles, again, any number you like, but I'll choose 20 for consistency. And this time we can see that rather than drawing rectangles, the left and the right-hand side of each of these little strips has been joined by a straight line, which is a fairly good approximation. Here, if I zoom up a bit, here our trapezium is slightly higher than the value of the green line, the curve. This one here, it's very close to the same, although not exact. Up here, our trapezium is an underestimate. We've missed a little bit. Same here. Well, hopefully, the under and over estimates will counterbalance somewhat, and we get an area 23.74. Remarkably close to the actual area of 23.72. Again, the nice thing about this, trapezoids are very simple to calculate, especially for a computer. And again, we don't have to limit ourselves to 20 little strips here for the interval. We could make that 200 or 2000 if we wanted to. 2000 is probably a bit much. Let's see what we get. Of course, we can't see the individual strips anymore, but look at that. We have exactly, well, at least 2 decimal places, we have the same answer as the definite integral. So numerical integration is certainly a technique worth knowing about. Numerical integration gives us the answers that we require, and especially, not so much in this case, but in cases where we have functions which are too difficult to integrate algebraically. Numerical integration gives us the answers we need to solve the problem that we're working on. Well, that's it for now. That's just a very quick demo of how to use GeoGebra to demonstrate the trapezoidal rule, the Riemann sums, either left, right, or midpoint, depending on the value of that last parameter in the function, or, of course, the definite integral. And that's the exact answer you would get from algebraic integration. Thanks very much. See you next time.